Hi everybody. I wondered what would happen if you took a linear feedback shift register by using a modified twisted ring Johnson counter. And as it turns out, it has interesting properties. As you may recall, the twisted ring counter uses the inverse of the last stage as feedback, and the linear feedback shift register uses an exclusive OR. So what we're going to do is combine both the linear feedback shift register tap with the inverted output, making a twisted linear feedback shift register. And the way you do an analysis on something like this is you write out all possible present states: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and then you proceed to write out the inputs to the flip-flops: D sub A, D sub B, D sub C, and it's pretty trivial to see that D sub C equals B, so if you look at B, you can just write it out: 0, 0, 1, 1, 0, 0, 1, 1. If you look at D sub B, well, it must be equal to A, so you can write that out. And it looks like everything else is 0. And the only thing that's not trivial is that we're working with C prime. Right, there's C prime, exclusive OR with B. So here's B. If C prime is equal to a 1 and B is equal to a 1, then the output will be 0. So here the 2 would be 1 and the output would be 0. So if I see 1, 0, it'll be a 0. If I see C is equal to 0, that makes it a 1 because we're working with C prime. So if we see a 0, 0, then the output will be 1. Similarly, if I see B is equal to 1 and C is equal to 1, then we can output a 1. But if you look at the, well, here, let's just draw a truth table just to be clear. B, C, 0, 0, 0, 1, 1, 0, 1, 1, C prime, 1, 0, 1, 0. And now we can write A, B, exclusive OR C prime. And so that's this, exclusive OR with that. And so it's going to be equal to 1, 0, 0, 1. And so if we find 0, 1 anywhere, the output will be a 1. So here's 0, 1, and the output will be a 1. Here's 0, 1, the output's a 1. And now we can write out the present state, next state diagram: A plus, B plus, C plus. And this will be equal to the inputs on the D flip-flops: 0, 1. Output should be a 1. 0, 0. Output should be a 0. So here's 1. 1, 0, 1, right? 1, 0, 1. The output should be 0, 1, which means you're going to have a 0 here. So that says to me if I start with 0, I'll end up with a 4. At stage 4, I'll end up in stage 6. After stage 6, I'll end up in stage 3. After stage 3, I'll end up in stage 5. After stage 5, I'll end up in stage 2. After stage 2, I'll end up in stage 1. After stage 1, I'll end up back in 0, which is to say, I'll end up here. Well, what happened to 7? 7 loops to 7. So now instead of 0 looping to 0, we have 7 looping to 7. So in principle, we really haven't changed things very much, but we've made it so that now you can start in 0 instead of starting in something that's not 0, just by virtue of using the inversion. We still get the same pseudo-random number behavior, only we have a slightly different sequence. Thank you.